Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue the discussion on sequences and series in Java. And in the last video, we discussed how different transformations such as Aitken, Shanks, and then Richardson help accelerating different types of sequences. And the key point was that if we are summing over an alternating sequence, a sequence that has alternating signs in its terms, it's definitely better to use Shanks or Aitken transformation. But then if the sequence is not alternating in sign and we're trying to sum the terms of the sequence to find the series, it's better to use Richardson transformation. And we said that Richardson, it could be first order Richardson, second order Richardson, third order Richardson, or fourth order Richardson, and etc. And this slide shows the comparison that we did for the 1 over k squared sequence, and we're summing from 1 to infinity. This sequence definitely converges. How do I know? Because the error goes to 0. How do I know? Because I can approximate the error. So how do we approximate the error? The error of a partial sum is summing from n to infinity of 1 over k squared, which I can approximate with the integral of 1 over x squared from n to infinity, which is 1 over n, right? So this series behaves as the limit plus a1 over n plus a2 over n squared, etc. And it's a monotonic series. It's very obvious that this is a monotonic series, and the partial sum converges to the limit because the error goes to 0 as n goes to infinity, and the limit approaches L, this partial sum approaches the limit from below because all the terms are positive. So as we add up more and more terms, the sequence gets larger and larger. So Sn is always less than L, right? So all these terms, A1, A2 coefficients are positive in some sense, all right? And we showed that if we look at the comparison of the Aitken and Richardson, this is the plot for Aitken, and we saw that Aitken doesn't really, even if we apply Aitken even 3 times, it doesn't give us a good acceleration. The original sequence is the blue curve, and it has like 1 decimal place of accuracy, and after 3 Aitkens we get like 2 decimal places of accuracy, which is not good. On the other hand, if you use Richardson transformation on this sequence, we see that when I say on this sequence, it means we apply the Richardson on the partial sum sequence, okay? Not on 1 over k squared. We create a partial sum sequence Sn, which is summing from 0 or 1 to n an, which is 1 over n squared or k squared. And then that's the partial sum. That's the sequence that we're trying to accelerate for convergence. We saw that the first order Richardson immediately gives us about 3 decimal places of accuracy. The second order Richardson gives us 5 to 6 decimal places of accuracy, and the third order Richardson gives us more than 8 to 9 decimal places of accuracy. So for this type of sequence, 1 over k squared, Richardson is definitely much better than the Aitken, right? Aitken or Shanks are hopeless, but Richardson is much better. And the question is, how do I know if you give me a sequence, a series, right? 1 over k squared or any type of an, ak sequence. How do I know which one to use, Shanks, Aitken, or Richardson? So the key here is understanding the behavior of the error, right? And before looking at general case of how the Shanks, Aitken, or transform come to be, these type of accelerators, let's try to look at another example. In this example, I take the 1 over k squared, but now I add an alternating term, right? Minus 1 to the k plus 1. So it's like 1 minus 1 over 2 squared plus 1 over 1 over 3 squared minus etc. Okay? So now I take the 1 over k squared sequence and then add an alternating sign term to it. This is an oscillatory convergence, right? Because if you look at this sequence of the partial sums, they oscillate around the limit. And however, this series exists, which means the partial sum sequence must converge. How do I know that? Because again, regardless of whether or not we have this alternating sign term, minus 1 to the k plus 1, I can estimate the error by integrating 1 over x squared. So the behavior of the error is still 1 over n, right? But the coefficient could be positive or negative. And we are going to do exactly the same thing here. We're going to take this and run Aitken and Richardson and see which one provides a better case, a better convergence. So let's head to Eclipse, and I have this test Richardson, which was 1 over k squared. So let's copy it and create a new class. Let's call this Richardson 2. And in the Richardson 2, what I'm going to do, I'm going to create basically minus 1 to the k plus 1 power. So basically what I want is if k is even, I want to get if k is even, I want to get minus 1. K is odd, I want to get plus 1. Because I'm summing from the k equals 1, so I want the first term to be positive. So what we are going to do here is that k mod 2 equals 0. We're going to compare it. And if k is even, I want to have minus 1. Otherwise, I want to have plus 1. Okay? And remember, just note this one important thing, that I'm returning double values, not integer, because I'm dividing by k is long. So if I return 1 as an integer and then k is long, k times k is also long, and 1 divided by k squared is always 0, which is incorrect, right? So we should either return a double, minus 1 plus 1, or convert k to double before calculating this rational number. Okay? And we don't know the exact value, so I'm going to just look at the absolute value of the sequence. Basically, I set the exact value to 0, which means I'm just looking the absolute value or the magnitude of the terms of the partial sum or the Richardson. Okay? And we know that this sequence converges, and so the exact value is 0. Everything else is the same. I'm just going to, because I'm not looking at the error, I'm just going to remove the log. I just comment them. I just want to, on a linear scale, I want to look at the how the Richardson and the Aitken are accelerating the convergence here. Okay? So test 1 is Aitken transform. We're applying Aitken transform twice to the or 3 times to the partial sum. So let's see. Test 1 is Aitken. Okay, and okay, I need to remove the log scale from the Aitken 2. And maybe let's increase the font to 15, the font size. Alright, so obviously the blue is the original sequence, and we definitely see the oscillatory behavior, but that's a convergence behavior, right? The terms are oscillating around the limit, the terms of the partial sum. And as you can see, the first Aitken is the red one, and we see that it has a much better behavior, almost converging after just a few steps, 8, 9 terms. Okay? And even the higher order Aitkens, the green one is the second order or the second Aitken transform on the first Aitken, and then the black one is pretty much converges. So you see that after 3 Aitkens on the original sequence, the black one, you pretty much after 2 terms you're there, right? The error is very small. So let's zoom in as much as we could, as much as we can. The red is the second Aitken, the green is the The red is the first Aitken, the green is the second Aitken, and the black is the third Aitken. So the limit is about 8.22467. Okay? So 0.822467. So I can write it here. 8.22467. Okay? As the exact value. We can zoom in and okay? And now I can look at the error. So the black one, so as we can see, the sequence has a very slow convergence rate, and then the red one is getting better. So the first Aitken is better. The green and the black pretty much converge after 20 to 30 terms. Okay, let's put this back, just look at the terms. 0. So this is Aitken, and we see that the Aitken is definitely helping a lot in terms of the convergence of the sequence. Let me just zoom in. Alright, so we're going to copy this, put it in our slides. So this was Aitken. Now let's see what Richardson does. So for Richardson, I'm going to run test 2. And it's very interesting that not only so the blue is the original sequence, right? Just summing up the partial sum. And the red is the first Richardson, first order Richardson. It actually gets worse and worse. The green is the second order Richardson, and the black is the third order, which is definitely diverging. So not only Richardson doesn't help, it actually causes the sequence to diverge. So Richardson is definitely not a good option in this case. Definitely we don't get a good not only we don't get any convergence or any benefits in terms of faster convergence, but in fact it diverges. Remember, the blue here is the original partial sum sequence, and then the red is the first Richardson, the green is the second Richardson, and the black is the third Richardson, which pretty much diverges. Okay? So just be careful when you're trying to sum the sequences. Just try to get a feeling for the behavior of the error, and if it's alternating in signs, if it's oscillatory, definitely by oscillatory I mean the sequence that is generating the partial sum, this AK. Okay, if this is oscillatory, we know that the partial sum is also oscillating around the limit, and then we should use Aitken or Shanks. If it's a monotonic, then we should use Richardson. Okay, so then the next question is where are these accelerators come from? What's the reasoning behind this? And in order to do that, I'm going to present this discussion. So the question is, where do the ideas of Aitken, Shanks, or Richardson acceleration come from? And these are based on modeling the asymptotic behavior of the error. So this is very important, modeling the asymptotic behavior of the error. And it's not an exact modeling, it's just based on intuition, how the sequence would behave, right? If we have an alternating convergence, what happens is that we know that we have to use Aitken or Shanks, right? Aitken or Shanks. But why? Because typically in physics or in engineering problems, this type of sequences, the way their error, if you try to estimate the behavior of the error. So we have a sequence that is alternating around the limit. We know that it converges, and the terms of the sequence as we increase n, they are alternating between the limit, but they are getting closer and closer. So this is like an oscillatory behavior. And typically in physics or engineering problems, you can model the behavior of the error with something like this: some constant times minus b, another constant, to the power of n. So the error behaves like some power of n, right? Some constant to the power of n. And obviously, in order for the error to go to 0, this b coefficient should be less than 1, right? And this a coefficient could be positive or negative. We don't really care that much. But then if this is in fact the behavior of the error, what we can do, we can say, okay, an is asymptotic to the limit plus a minus b to the n. And now I can write the same thing for an plus 1 is asymptotic to l plus a minus b to the n plus 1, all right? Now if I bring l to the other side, an minus l, an plus 1 minus l, okay, and then divide these two, I get minus b equal to an plus 1 minus l divided by an minus l. And I can do the same thing for n terms, the nth term and n minus 1 term, right? Again, bring the l on the left side, an minus l divided by an minus 1 minus l, and it gives you minus b, all right? So that basically means that now if we set these two equal to each other, then we have eliminated a and b and have come up with a relation between the l, the limit, an plus 1 and an minus 1. And now I can actually solve for l, and l is an squared minus an plus 1 an minus 1 divided by 2 an minus an plus 1 minus an minus 1, which is exactly the Shanks, right? If we go back and look at the definition for Shanks, Shanks is if you write Shanks is an plus 1 an minus 1 minus an squared divided by n plus 1 plus an minus 1 minus 2 an, okay? So that's basically the same thing. I just reversed the signs of the numerator and denominator. So n plus 1 times an minus 1 minus an squared, and then an plus 1 plus an minus 1 minus 2an. This is Shanks. And then it turns out that now the error of this, if you look at this sequence and just substitute this term, this approximation, the original approximation, l plus a times minus b to the n. Now consider this as a new sequence and substitute this model into this. What you will see is that this becomes asymptotic to L plus some constant, now b to the n plus 1 power. So that means you actually reduce the order of error. And now the convergence becomes faster and faster, right? Because instead of b to the n, remember b is less than 1. Instead of b to the n, we end up with b to the n plus 1. And that's very important because now we have bn plus 1. So the convergence faster, or the error goes to 0 faster. And because this is a new sequence which follows exactly the same model again, then we can do Aitken and Shanks again on this new sequence. And from bn to the plus 1, we go to bn plus 2. And this sequence could, in fact, continue indefinitely. So you get arbitrarily fast convergence, right? The problem is that at some point, usually after 3 or 4 times of applying Aitken or Shanks consecutively, it becomes unstable for large n. So it is always advised to do only like 3 or 4 times of Aitken or Shanks, as we have done before, right? So we have never done anything more than like 3 or 4, and we saw that for this sequence, which has this sequence was 4 minus 1 to the k 1 over 2k plus 1. So when k is large, the terms of this sequence are 1 over k. And the error of the series is integral of 1 over x, which is log of x or log of n. So log of this is usually the worst that can happen, right? The slowest convergence or the slowest error rate. And we saw that 3 Shanks or 3 Aitkens are more than enough after 20 summations, 20 terms. We get 9-10 decimal places of accuracy. So this is more like the worst case. If I have 1 over k squared, obviously we need less terms to sum to get a good accuracy. So typically 3-4 times of Aitken or Shanks is more than enough. Okay. Now the same thing with Richardson. So if and again, what we did here, we transformed the sequence by solving for L. Remember, the base idea was to try to model the error of the convergence, a simple model, and this behavior only applies when the model is in fact something like this, some number to the power of n. Okay, and what this transformation does is it removes the b to the n, and the result of this transformation has a term of b to the n plus 1. So what we are doing is that we are eliminating poorly converging leading terms of the error. All right, so we heuristically model the error with something like this, b to the n, and find a transformation so that the transformation, when we plug this model, it ends up with b to the n plus 1. And then we say that, okay, now it has a faster convergence because the error goes to 0 faster, because the leading error term now has been eliminated. Okay. Now what happens in the non-oscillatory behavior? Let's say we go monotonically to the limit from above or below. And typically this happens in physics or again engineering problems. This kind of behavior has an error model of some constant over n to the b, where b is let's say greater than 1. And if you remember, we actually have seen this before when we discussed numerical integration, and we saw that for for rectangle approximation of numerical integration, for rectangle approximation, the error was proportional to 1 over n. And for trapezoid, it was 1 over n squared. For Simpson, it was also 1 over n squared, etc. So in those cases, we can model the error as 1 over n to some power, which is typically greater than 1, greater than or equal to 1. Okay? And then when that's the case, then the question is, obviously this behavior doesn't work, but we can again follow exactly the same rule, but in a different way. So the way it works is that we write an as L plus a over n to the b. Remember, the ultimate goal is that to try to come up with a transformation that has a better convergence. A better convergence means I want to come up with a transformation of an that when I plug this definition, this limit plus the leading error term, the leading error term goes away and I end up with some constant over n to the b plus 1 at least. It's better to end up with n to the b plus 2 or etc. So if you have a uniform convergence, something like this, usually or typically in the engineering or physics problem, we do Richardson. And so the way we try to transform this sequence is that we write the n terms, L plus a over n to the b, and then we multiply it by n. And we also write n plus 1 term. N plus 1 times an plus 1 is n plus 1 L plus a to the n plus 1 to b. And then nan is also nl plus a over n to the b. And when you subtract this, both sides, we have n plus 1 an minus n plus 1 an plus 1 minus nan. on the left side. On the right side we have n plus 1l minus basically minus on the right side we have nl plus a over n plus 1 to the b, right? Then if we when we subtract, we have n plus 1l and nl, so we end up again with l. So n plus 1 times an plus 1 minus n times an also has a limit of l, right? It converges to the same limit as the original sequence. But then once you look at the order of the error, it actually is 1 over n to the b plus 1 instead of n to the b. And that's exactly why we define the first order Richardson as n plus 1 Sn plus 1 minus n Sn. This, if the error of convergence has a behavior of 1 over n to some power, this transformation makes the error some constant over n to the original power plus 1. Now the error goes to 0 faster, okay? Now with the same logic, we can eliminate 1 over n to the b and 1 over n to the b plus 1. If the error has also 1 over n to the b plus 1, we can eliminate these two, the first two leading terms of the error simultaneously by applying a second order Richardson instead of the first order Richardson. And if we want to eliminate simultaneously the three leading terms of the error, we use the third order Richardson, and etc. So you see the power is it's a very powerful concept, because if I have my error is 1 over n plus 1 over n squared plus 1 over n cubed, or some coefficients there, but the three leading terms are something like that, I can apply a third order Richardson and immediately get rid of those three first terms of the error. And now the transformed sequence has an error, leading term error of 1 over n to the fourth, which is a huge improvement. So that's how, for example, if for numerical integration, if we start from trapezoid method and then apply a third order Richardson, suddenly the convergence is very fast, and then we have a very fast convergence. And we discussed this at some point, and this is called Romberg integration. So the Romberg integration is exactly like this. It starts with trapezoid and then applies Richardson extrapolations, and it gives you a very beautiful and fast convergence with you don't need to have many, use many sub-intervals. So the number of sub-intervals could be in fact very small, maybe 10, 15 is enough. But you apply third order or fourth order Richardson, and then suddenly the error goes down very fast. So this is the idea behind this transformation. And again, not all sequences, not all problems, we can model them like this, but if we have some intuition that the error eventually behaves some number to some power, or the n to some power, we can use either Richardson or Aitken or Shanks, okay? So this is the idea. And then another interesting thing about, now that we know about sequence transformations, another interesting thing is perturbation theory. And I'm going to talk about this in the next lecture. So stay tuned. Thank you, and I'll see you in the next one.